So, welcome all of you. In the last 1 or 2 classes, we have been discussing about nuclear over-Raster effect spectroscopy. I introduced concepts and what is NOE and what are the factors that govern NOE, and we discussed varieties of conditions, what will happen to the NOE, whether there will be a gain or not at depending upon omega TOCSY. And we arrived at 3 conditions: omega TOCSY greater than 1, omega TOCSY less than 1, omega TOCSY approximately equal to 1. And we said at omega TOCSY equal to 1, approximately equal to 1, NOE will be 0. In other 2 conditions, extreme narrowing conditions and diffusion limits, there will be NOE positive and negative accordingly. So, we discussed a lot of the things about it, and also we arrived at the relaxation phenomena, in the sense dipolar relaxation which is responsible for this NOE, and where are these fluctuating fields coming from. Then we arrived at j omega, and then the spectral density function depends upon the omega, of course also probability of the transition W1, W2 and W0. And then we also discuss about this fluctuating field because of the molecular motion, which depends upon TOCSY correlation time, and also on the spectrometer time, normal frequency, spectrometer frequency. So, then varieties of factors are responsible for this. We discussed everything, and then at the end we arrived at the equations for NOE enhancement, and we saw NOE enhancement would be for a homonuclear spin in the extreme narrowing condition will be about half. That is what we saw that in the case of homonuclear. For a heteronuclear case, we also saw that depending upon the ferromagnetic ratios, the enhancement factors will be different, and we saw even up to 1200, 1500 times enhancement we saw in some of the heteronuclear case, where proton is the irradiating spin. So, all these things we saw, and then we found out varieties of possible NOE experiment. For example, steady state NOE, where we are going to selectively irradiate a peak at a low RF power, and then do another one with the equal RF power at a far off place, far off resonance, and take the difference between 2. And if there is any NOE enhancement for any of the particular spins which are close by, that gets reflected in the spectrum, in the difference spectrum. That is a steady state NOE. We saw 1 or 2 examples of that. And also next is transient NOE, that is a 2D NOE. We discussed a lot about 2D NOE, what is 2D, how do you get the 2D NOE spec, everything. And then we discussed more about ROSY also. ROSY is a rotational frame over-Raster effect spectroscopy that is done and favorable for molecules when omega TOCSY is approximately equal to 1, where you do not get NOE, whereas ROSY always gives positive NOE. That is an advantage. So, we took 1 or 2 examples of ROSY, and what are the complications involved in NOESY, ROSY and all these techniques, including steady state. What happens if you do not have a selective excitation where frequency not proper? What happens if the multiplet peak of the coupled spin, entire multiplet region is not selectively saturated, what will happen? So, varieties of problems, complications are there. In all these experiments, some type of complications are there, and we know how some of these can be overcome. That also we discussed. And then coming to 2D NOE, we discussed the pulse sequences, and I told you if we are going to cross peak which is symmetric with respect to the diagonal, we discussed that. And then we started even getting the application of that to find out how NOESY can be used on some simple molecules. And we took 1 example to see how this NOESY helps in getting the conformation of that molecule. With that, we will continue further today. We will take few more examples of NOESY, how 2D NOE can be utilized to get the structure of or conformation of the molecules. Some of the molecules, some simple to relatively complex molecules I show. That is the important condition, because basically in this course I wanted to tell you about how we can analyze the spectrum, how we can use the different NMR techniques 1D and 2D to get the structural information for your molecule. Okay, we will start with another molecule today. We did cis-pentene yesterday in the last class. Now we will start with another molecule here. This is the molecule, some name for it, trans 2 actin 4-1 in 4ON in DMSO. This is a NMR spectrum. This is a COSY spectrum. Of course, very easily you can interpret the COSY spectrum. You can always start to CH3, as I always tell you. Proton H8 is there. That is a triplet because of this, and then this will be triplet because of this, and this will be triplet because of this, and very easily you can interpret it. But anyway, COSY is going to help you in identifying all the peaks. Start with that one. Here we have taken from H2 proton, okay, H2 and then which is correlated to H3 here, because this is an isolated pair, isolated spin system. You can see that, and there is a lot separation between CO is in between, and there is no coupling between this and this. So they are all forming an isolated pair. 1, 2 and 3 are isolated pairs spin system, and this is another spin system. There are two spin systems here which COSY will easily identify. So this is what we started with one of them, H2, and then it correlates to H1 and then also to H3. And of course in this region you can identify from a methyl peak, and of course there is a cross peak H8 to H7, and then of course other also 6 and 5 you will get the cross peaks. So easy, this is a crowded region. I didn't explain this is very easy. I assume that I know how to make the assignment by using COSY, ascend all the peaks. My main idea is to get the conformational information for this molecule using NOESY. This is NOESY spectrum of the same molecule. Of course, you will see that the peaks will be not exact identical to COSY, because there will be additional peaks coming because of the NOESY. Again, we can see there are correlations here from proton 3 to proton 1, and proton 3 proton 3, where is proton 3? Proton 3 to proton 5 here. What does it tell you? See, with proton 1 is correlated to proton 3. This is possible only when these two are on the same side of the double bond of this double bond. Similarly, CH2 is correlating to H3. That also implies that these two are on the same side of the double bond. So these correlations are seen here. This is a correlation H3 to H1, and then you also have H3 to H5. Both are being seen here, and this puts them, this CH3 and CH, on the same side of the double bond. Okay, and further, if you can also see the correlation between H2 to H1, which is this is H2 to H1 is there, and H2 to H5 is also there. That you can see here, H2 to H1 and also H2 to H5. What does this say? That means these are all on the other side of the double bond. So this clearly tells you the NOESY cross peaks tells me this cross peak between these two puts them on the one side of the double bond, and cross peak between 2 and 3 here, and of course 2 and 3 are trans to each other across the double bond. This confirms that alkene protons 2 and 3 are trans to each other, because these are one side, these two are on one side, from the correlation information what we got from the NOESY spectrum. Okay, the question is, if the alkene were to be cis, what would have happened? This instead of trans, we know correlation is between this and this and between this and this. That's why we said these two are trans to each other and these are on one side of the double bond. That's fine. If they were not trans, what would have happened? If it were to be cis, then you would not get H2 to H5 correlation. This correlation you will not see, and you will not get H3 and H1 correlation. If it is on the other side, the distance becomes more, you will not get the correlation. So these type of correlations, what we observe for this molecule, puts these two on one side and these two on the other side of the double bond, and establishes cis geometry for the alkene group of this molecule. Okay, for the alkene protons it establishes cis geometry. This is how we can understand very easily, we can interpret it. We will extend further how we can get the information about the substitution at a particular site specific substitution if it is there in phenyl groups, how we can use NOESY. For that I have taken the example of 3-fluoro-4-methoxy acetophenone. This is the molecular structure. We want to see, our main idea is where is this OCA3 and where is this one with respect to fluorine. This is, or in other words, we need to get the structure of the molecule. Where is the position of fluorine, this and this with respect to that. That information about the structure we should get. We can use various methods like COSY, NOESY, everything will adapt. Now the first is, you have to get a proton NMR spectrum. We need to analyze that. Of course, this analysis is not a rocket science, very easily you can understand looking at this one. Of course, this proton 8 is COCH3, CH3, and of course proton 9 is OCH3 directly attached to this one. This is a methoxy proton, this is just CH3 groups, and this is here, H8 and H9, and both of them are singlets. There is no long range coupling to this. We are seeing, maybe there we are not seeing it. And the remaining thing is only these 3 protons, 1, 2 and 3, and they are all coupled to fluorine. Remember, fluorine is a spin-off nuclei, 100% abundance. So fluorine proton couplings are reflected in this spectrum. So looking at the spectrum, you can try to understand, make the assignment which proton is which. Very easily you can do that. If you look at this one, this experiences only one ortho coupling. It has to be a doublet. This one experiences only one coupling with fluorine. It has to be a doublet. So for example, if you look at this one, this can experience a meta coupling, this can experience a para coupling. We can see varieties of things. So best thing is, we will expand this and see the spectrum. This is a proton spectrum of these 3 protons expanded. Look at it very easily. You can identify which is which. This is proton 5. The proton 5 is here. Why it is a triplet? Of course, this has one ortho coupling with this and also meta coupling with this. If both of them are nearly equal, it should be doublet of doublet, or if they are equal, it will be a triplet. So this could be H5 because it is equal. Come to H2. H2 has one ortho coupling with fluorine and a meta coupling with this. Para coupling may be or may not be seen. So it is a doublet of a doublet. I can clearly say that is H2. What about H6? H6 proton will have ortho coupling with this and a meta coupling with this and also a para coupling. In principle, it should be doublet of a doublet, 8-line pattern. Large doublet is because of one of the ortho couplings and then coupling with the fluorine and then with this one. Okay. To simplify the problem, what we can do is, we will do the fluorine decoupling. That is also possible. Heteronuclear decoupling we can do while observing proton. When you do the fluorine decoupling, what will happen? We are going to break all the couplings of proton with fluorine. Only we will get HH couplings. FH couplings are completely removed. That is what we do. Broadband fluorine decoupling of the proton spectrum. And this is the fluorine decoupled spectrum. If you look at it, H5 is a doublet. Obviously, this has to be this. Only one bond ortho coupling. I mean, 3 bond is there. 3 bond ortho coupling between 5 and 6. Then H2. H2 is F coupling is broken. Then it is only a meta coupling. So this is with this. So I can clearly or conclusively say that is proton 2. Then what about the other one? Other one is proton 6. Proton 6 is very easily you can identify. This is proton 6. It has one ortho coupling and one meta coupling, doublet of doublet. Large doublet is because of ortho coupling and small doublet operation is because of meta coupling. Very easily you can do it by doing the fluorine decoupling. Same thing if with little experience we can do without decoupling also, fluorine decoupling, but this simplifies the spectrum. So now we have made the assignment of proton 2, 5 and 6 from the for all the 3 protons in the proton spectrum using both fluorine decoupling and non-decoupled spectrum. And this is the spectrum, and this comes because of J ortho I told you, J meta, this is J ortho plus J meta. As that is the reason why, remember when I analyze the phenyl group proton spectrum of the molecules containing phenyl groups, multiplicity pattern how it comes I explained to you based on ortho coupling, meta coupling and para coupling, what type of pattern we get. Using that knowledge here we can completely make the assignment. Alright. From the coupling pattern and using this one also, we know this compound, look at it, this one ortho, one meta and one ortho and meta coupling is there. How this type of spectra splitting arises? From this you can come to a conclusion, this must be 1 to 4 trisubstituted, because here look at it here, if it is 1 to 4 trisubstituted, see what will happen, this is 1 and 2 and 4 trisubstituted. If that is the situation, only then this pattern will come. Because of ortho meta para coupling what we saw here, this pattern is possible only if the substitution is 1 to 4 trisubstituted benzene. Which substituent is in which position is a different question, but the 3 places at which in the phenyl group their substitution comes is at 1, 2 and 4. Okay. Then find out the possibilities. We know the structure of this molecule is given. There are various possibilities. 1 to 4, this could be one possibility. 1, 2 and 4, fluorine instead of here could be here, and 1, 2 and 4, fluorine is here and these two are ortho to each other. Think of all the possibilities. There are 6 such possibilities we can think of. If for 1 to 4 substitution, where one is fluorine, other two substitutions are OCA3 and double COCA3. Okay, this is the situation. So there are 6 possibilities. We'll think of that. Now let us look at the NOESY spectrum. Assuming that we know already assignment have already been made. Let us look at the NOESY spectrum. NOESY gives Ca3 protons show correlation to 2 protons H2 and H6. We have already made the assignment. This is H2 and H6 here. Okay. See this one. H2 and H6 both are close by. And NOESY is giving me cross peak, especially the Ca3 proton. This is the Ca3 proton, not OCA3. OCA3 comes downfield, I told you. So this Ca3 proton is giving cross peak to 2 protons. That means, what is the conclusion you are going to draw? This tells me that this group must be between 2 protons of the phenyl group. It cannot be one like this. It is not possible. It cannot be here because other side is this one. It must be between 2 protons of the phenyl group. That because of the correlations 2 and 6 are seen for Ca3 group. This places the acyl group between 2 protons of the aromatic group, aromatic protons. So what are the possibilities you think of? There are 6 possibilities. Then if this has to be between 2 protons, then this is not possible, this is not possible, this is not possible, this is not possible. So all 4 possibilities are ruled out. Then we are left with only 2 possibilities. Because of Ca3 is giving cross peak to 2 protons, either this should be this or this. Only here this position is changed, that is all. That is the only possibility where OCA3 can be between 2 protons. Now there are 2 possibilities. We will go further down. Look at the NOESY spectrum again. We look at OCA3 protons. OCA3, this proton gives cross peak to proton 5, which is at 7.2, this one. See, it is giving a cross peak, OCA3, this is OCA3. See, from diagonal come here, go here and then come to this square. So this OCA3 is giving a cross peak to only one phenyl group proton. That means, what is the possibilities we can think of? Then this will be the only possibility. Fluorine is on the right side, it is not giving correlation to that. So that means, if you look at if you consider this possibility, already we have eliminated this. Now this is also eliminated, because if this is the fluorine, OCA3 cannot give correlation to this. If this is the only possibility, it can give correlation to this. So fluorine cannot be here. Fluorine has to be on other side here. It cannot be here. Okay, that's what is the conclusion. So this also is ruled out. Then what is the OCA3 protons must be ortho to H5 proton. That's what the conclusion. Otherwise, OCA3 cannot give correlation to this. So OCA3 proton is ortho to H5 proton. Using this NOESY information, we can draw the conclusion now. This is the structure of molecule, because we understood this is between 2 protons and this is giving cross peak to this one alone. That confirms me this is the structure. All other possibilities are ruled out. So beautifully, using the NOESY, you can get the conformation. I hope you got your point. We will go further. Let us look at the another molecule. This is a molecule. We will use all the allowed techniques, possible techniques in 2D, like COSY, HSQC, HMBC, NOESY, etc., and get the structure of the molecule. I am showing you all these things, but if you are a little bit of experienced person, if you already worked in NMR for couple of weeks or months, then all you don't require. 1D NMR, COSY is not required, HSQC is not required. Looking at the simple molecule and proton NMR spectrum, it will be fairly easy enough for you to analyze and get the information. But to make you comfortable, to comfort all of you, I am going through all this 2D spectrum, so that you know what are the steps you have to follow to analyze the spectrum. Of course, this is a proton-proton COSY. Very easily you can do that. This is proton 1. This is CH3CH2 in isolated group here. So the proton 1 can correlate. This is triplet and this is a quadret. This is correlated to this. This is only isolated group, no other correlation. So COSY identified this, and then next is this one. we start with this OCH3, this is OCH3, come down and it correlates to 2 protons which are here. And again this is correlating to one of them, this will correlate within itself the other one. So 4 and 5 are correlated and both of them are correlated to 1. Very easily you can identify which is which. And of course further, to find out the number of carbons and everything, whether it is CH2 proton or CH3 proton, because we need to identify whether CH2 or not. By looking at the multiplicity pattern, triplet and quadruplet, you know one is CH, other is CH3. Just to make you understand, where we can utilize multiplicity edited HSQC spectrum. If you do that, you see the opposite sign here. That tells me H2 proton must be CH2. Okay, very easily you know that. Fine. That is what it is. And you know the correlations from this, which are the carbon chemical sheet, which are the correlations, everything you can identify. There are only 5 protons here, 5 different correlations we are seeing. Of course, this carbon you are not going to see. Confirms there is one CH2 by this multiplicity rated HSQC. Of course, we can also do HMBS to get the correlation of carbon-carbon correlation. Of course, that is not needed if you want to get the structure. I am looking at only whether this position is, whether this is trans to each other or cis to each other. For that we do not require HMBC, but for the sake of showing I am showing you. These are all, there are sometimes it so happens you will get large class peaks which are widely separated like this. They are all one bond HSQC correlations, they are not efficiently filtered out. In HMBC I told you one bond HSQC correlation peaks are filtered out. But if they do not filter out efficiently, you see all of them here. There are 4 such correlations are seen here. All right. And then you can see HMBC H1 is correlating to C2, this is correlating to C2, and H1 is also correlating to C3. This puts them as one side, on one side of the C double bond O. Okay, these correlations. H2 is also correlating to C1, H1 is correlating to C2. H1 is correlating to C3, H2 is correlating to C1 and H2 is also correlating to C3. So, varieties of correlations you can see. This idea places me, puts the CH3 CH2 on one side of C double bond O. That is what we can say. We can say CH3 CH2 is attached to C double bond O from these correlations, my HMBC correlations. I hope it is clear for you. So, remember there are correlations. What you have to see here is, this is correlating to this carbon, this is also correlating to this, and this is correlating to this carbon, this is like this. This makes me give idea that CH3 CH2 is attached to C double bond O. All right, we will go further. Now we can also see H4 correlating to C6, H4 correlating to C6, H4 correlating to C2, H4 correlating to C3, all correlations we can see. Similarly, H5 correlation, 3 carbons it correlates. Similarly, H6 correlated to 3 different carbons. All this tells me that this group is on other side of the C double bond O. If you carefully go through it one by one, slowly we can see that one. But anyway, that tells me that now there is a C double bond O, this is on one side and this is on one side. So, some sort of an information about the molecular structure is known. We will use the NOESY now further to get the confirmation. Basically what you need to come to know is whether these are trans or cis to each other. And if you see the NOESY, there are several correlations here. One, CH3 to CH2, this one is there, this correlation. H2 H1 correlation is there. And H5 H6 correlation and H4 H6 correlation is there. This is fantastic. These H4 H6 correlations here, they tell me, they are going to tell me that H4 H6 are one side of the double bond, whereas CH3 the H2 correlating to H1, they are on other side, and then further we are going to get H4 H6 correlations, H5 H6 correlations, H5 H6 correlations are seen, H5 H2 correlations are seen. See here, H5 H6 and H5 H2 correlations are seen. What does it tell you? All these 6 correlations, if you will see, it tells me this correlation. If you see H2 correlated to H1, H4 to H2, it tells me this is on other side of the one side of the double bond. Similarly, these correlations tell me, for example, H4 and H6 correlation tells me that they are on the, these two are H4 H6 tells me these are on one side of the double bond. So all these correlations tells me now this and this and this. Correlation H4 H6 indicate it is a trans geometry. H4 H6 correlation and this correlation tells me they are in the trans geometry. If they were to be cis, you would not have got H4 H6 correlation. Okay, so that's the thing. So this is what it is. This indicates the trans geometry for this alkene functional group. So now you know H4 H6 and H5 correlation would be absent. This one H4 H6 and H5 H2. This correlation would be absent if this group were to be cis, because this H would come here, then CH3 would be here, then this H5 and H2 correlation would not be seen. Similarly, H4 H6 correlation would not be seen because this will be trans to this one. This type of observations tells me that these two protons, alkene protons, are trans to each other and not cis to each other. So both observation of the peaks and non-observation, if in case if it were to be cis, you would not have seen that. So that's why we can come to a conclusion what is the structure or geometry of this molecule. We can go further for this molecule. Another one, this is a very simple spectrum. Look at it. We have proton 9. This is easily analyzable. We analyze this in the 1D, 2D, 1D and COSY also I remember. So we can start looking at the COSY spectrum. COSY spectrum identifies this one, H3 to H2 coupling, and from H2 we can go to this is number 8 and 9. 8 to 9 is then. So 9 to 8, 8 to 7 it comes, and then we here 7 to 6 is there. 6 you can go further and you will identify 5. From 5 you can go to 4, 4 to 3, like that. Entire all these protons could be assigned just systematically going step by step. I did this step by step. You can slowly see it. I will show you again. See, 9 is, I identify the peak 9 which I am confident. 9 I will go, it correlates to 8. From 8 it will go to 7. 7 to 6 is there. 6 to 5 it goes. 5 to 4 is correlated here itself, and 4 to 3 is here, and 3 to 2 here, and 2 to 1. Everything you can assign without any difficulty. Alright. Of course, multiply edited HSQC confirms how many CH2s are there. There are here 3 red peaks, you can see negative peaks. That shows there are 3 CH2s in these molecules. Okay. And of course, we can start looking at the HSBC, HMBC and make the assignment of all the proton carbon correlation here, H1C1 here, and then H2C2, H1C3. H1 is correlating to C1, C2 and C3, and H4 is correlating to C3, and H5 is correlating to C3, these both. So all this information, if a couple, you will find out what is what. Completely we can make the assignment of every peak here. Okay, as we will not go step by step, very easily. Of course, I have already told you how you can analyze the HMBC spectrum. Just I wanted to show that we can, using this HMBC and all this expanded region with all the correlations here, you can identify, get the structure of the molecule, carbon skeleton of the molecule. More than that, now you got the first proton assignment, carbon skeleton, carbon chemical shoots, everything. But finally what is left is conformation of the molecule. Here we use NOESY. When you do the NOESY, the H1 and H3 correlations are there here. See, H1 H3 correlations are there. H1 and H3. This correlation says they are on the same side of the double bond. If this was to be here, you would not see correlation for H1 and H3 if it were to be cis, because these two are on the same side of the double bond. You are seeing the correlation. So H1 H3 correlations are seen. Similarly, H7 H6 correlations are seen. This also tells me they must be on the same side of the double bond. When you say these two on the same side of the double bond, this must be a cis geometry. You have got the information already, and you can expand this further. You can see H1 correlating to H3 and H3 to H5. This is correlating to this one, and H2 is correlating to H4 here. See, this should be on this side. If it was to be if on the other side, it would not give correlation to H4. So all this thing indicates This is a trans geometry, whereas this is a cis geometry. You understand the point? Now, correlations of NOESY tells me this double bond, if you consider the proton 2 and 3, they are trans to each other, whereas looking at the correlation of 6 and 7, I can say proton 6 and 7 are cis to each other. In this molecule, H5 H8 correlation places here 2 CH2 groups on the same side of the double bond here. In addition to 6 7, we also see 5 8 correlation here. This 5 8 correlation you can see here. This is, so this tells me when I see that 5 8 correlation, these 2 CH2 groups on one side, 6 7 correlation tells these two on one side, and this correlation tells me these are on that side, one side of the double bond, and this two tells me they are cis to each other. So, varieties of correlation information we could get, so many correlated peaks. All these things put together in a nutshell, we can say this molecule has one double bond with a trans geometry and another double bond with a cis geometry. This is the structure of the molecule. So, we can get the structure of the molecule very easily like that. Of course, we can continue further in one more molecule, we will see that, and I will quickly show you. This is the 1D spectrum, very easily you can analyze this one, there is no difficulty. Assume take the cross peak, COSY peak here, this is the alphenyl group here in the COSY you can identify, and okay, this is the phenyl group, and NOESY if you go, I am sorry, okay, this is the phenyl group. Why it is going so fast? Okay, these two are correlated to each other. Okay, then there is a correlation among only these groups here. You can see that. All right, you can use multiplicity edited HSQC to identify whether there is a CH2. There is only one of them is the red color, negative sign, which tells me this C1, this H1 C1 is correlated, and H1 this must be CH2. Okay, with that information, now we go to NOESY. This is where clear information you are going to get. OH correlates to H1 here. This is a OH proton. It is this correlates to H1 here. OH is here. It is correlating to H1 here. You see, there is a correlated peak. These two are correlated. And then also OH is correlating to H8. This one. This tells me these two are on the same side, spatially close to each other. H3 correlates to H1, which is H3 here, H3 is here. See, H3 correlates to H1 and OH both. It also correlates to OH. When H3 is correlating to OH and H1, that means this CH2 and this proton are on one side of the double bond. This clearly tells me, this correlation tells me this CH3 is on the other side of the double bond. This correlation tells me CH2 and H are on other side of the double bond. So, like this you get the correlation information, indicates CH2 and OH on one side, and these two protons, this correlation tells me this is another side, this CH2. So, using this also further you can go H8, this one is correlating to H5 because these two are symmetric. I have not written here, but this is also same, these two. This CH3 is correlating to aromatic proton H5. That is clearly tells me these two are trans to each other, because there is a correlation between this and this, and there is no correlation between this and this. There is a correlation between CH3 and this proton, aromatic proton. All this tells me then CH3 and phenyl are on the same side of the double bond. So, this clearly gives me the idea about the geometry of this molecule, and this is the geometry. And there is no correlation between H3 and H8. This and this, there is no correlation because they are trans to each other. Very easily you got correlation between this and this, you got correlation between this and this, you got correlation between this and this. That is all. Very easily using this information you can fix the geometry of this molecule. That tells me CH3 and H are trans to each other. And of course, this is how we can analyze using NOESY a lot of structure of the molecules. And I think we took fairly good number of examples. What I am going to do is I will stop here. In this class we have taken several examples of simple molecules to show how we can utilize combined use of all the 2D techniques like COSY, HSQC, HMBC, NOESY. Sometimes all are not needed. In some cases you require it. Just if you are a beginner, you should go through all the things, all the spectra, so that you know how to go systematically. Or if you are already a person working with NMR and little bit of experience for a couple of weeks or months you have worked, you don't need anything. Just 1D spectrum or COSY will get some information. Straight away you can go to NOESY. Based on the correlation information, we could get the structure of the molecule. So we could get several examples of the molecule which has got a double bond, where you could get the cis trans geometry, and in the phenyl group we could find out the substitution position and rule out all other possibilities just by using NOESY. So these are some of the examples. I will stop here. We will continue with other few more examples and other topics in the next class. Thank you.